questions from homework stuff? Any left over from 6 or stuff from 7? I will say this, I don't know if I said this last time, but there will be a quiz on chapter 7 on Monday.
Next Monday?
Yes.
Good. On the chapter 7 early?
Yeah.
Okay. Yeah.
You can see what we have in our notes.
Degrees of numbers like that, right? The degrees of numbers. Like the 7.
Those are all coming out of our turkey coma or our tofurkey coma, whatever you prefer. I don't know if you go into a tofurkey coma, do you?
No, because they don't use that. They don't use the chemical. Yeah.
What's that?
They don't use tryptophan.
Oh, tryptophan. Well, actually, the last Mythbusters I haven't seen yet was talking about whether or not tryptophan actually, and it does. I mean, 'cause they actually use it as a sleep aid directly. Tryptophan. It's a good thing we got the next day off, unless you're going to be one of those crazy people out there for Black Friday.
Oh.
And there are already crazy people right now out there for Black Friday. Yeah.
For Black Friday, I know what I want to do. It's gonna be, yeah, I know that Black Friday is gonna be crazy, but I'm trying to find some friends to go with me.
Gotcha. You got to make a game plan. I actually have never partaken in any of Black Friday ever. I do Cyber Monday. I'd rather have the stuff come to me. Yeah. Instead of go out and battle. Some people live for that.
Get out of my way, I want the TV.
And then someone gets trampled to death every year.
Can you do number 10 on 7.2?
I got you. This is enough of your crap, Jeff. 7-2.
7-4.
Number 10.
Plus 31 here, so that's opposite.
Oh yeah. So this is so they give us a confidence interval in the way that the book really likes to write it. So this is really a question I could give if I just stripped away some of the statistics meanings and stuff. I can give this question to another math class, because really, where would p hat have to be? They ask you to put it in this form. Where does p hat have to be in that interval? It's got to be in the middle, because what do you always do? I take p hat and I add something and I subtract the same thing. So p hat's got to be right in the middle. So what's right in the middle of that?
60.
Yeah, p hat has to be 750. You have 30 away from each side, right? One way you could do it is these are 60 apart. Half of that is 30. Add 30 to 720, you get 750. So it's got to be right in the middle. All right, now how to get the error, then we actually just got it on the way. How much is 750 off from either side?
0.03.
0.30. Cool. That's all right. Well, that actually, you're right. 0.03.
Wow. Okay, so not.
You're fine. I'm crazy. So then how do I write it like this? I just put those together. Bless you. So then I'd say 0.750 plus or minus 0.030. Yeah. Cool. So there's several like that in there. They like to write either in this format or this format. That's how they like to put confidence intervals. So this is just more explicitly showing what the error is. We think it's 75%, give or take 3%. Right, that's really another way to look at that. Okay. So we do that all the time. How long do you think it's going to take you to do that? Like 10 hours, give or take a couple hours. I mean, you know, we give an estimate and then we give a range of how much we think we're off by. We do that a lot. All right. Any other questions from homework? Okay. No. All right. So we're going to get back into. Actually, we're going to start to get into chapter 8, but I do want to do a quick little review of how to use that chart. Just a couple quick things, especially because there are several people who aren't here. Have your T-score chart. First question really is, what two things tell me I use t-scores in a problem. What's the first thing I have to know before I do anything?
There's no z-score.
Say again?
It's a sample, not the population.
Missing z-score is missing. You use
Before I do anything, Z or T, what must I know? Normal distribution, 11. 1, normal. So that if it's normal, I could use a T or a Z, but what tells me specifically I have to use a T-score?
when it's sample population.
Careful.
Yeah, you can use.
So the sample size less than 30 would mean it's not normal unless they told me. But there's something else that tells me why were T-scores invented? They were invented to cover our ass for when we don't know the real standard deviation, the population standard deviation. That's why they were invented. So that's when I use them, when I don't know that.
The true mean. When you don't know the true mean.
So when sigma unknown, we only have S. Okay. Yes, sir.
I have a question on the homework.
Patrick, I love you. You're awesome. In this section or?
In 7.2.
Of course,
11.
Number which one?
11.
11, I'll tell you this, 11 is exactly like the one we just did there. It's exactly the same.
But the parentheses confuse.
That's all right. I could write this like this. Same thing. So you do the work the same way.
Alright, and then what I do is I divide it by 7.80 by 2720.
No. I think find the middle of two numbers. The most direct way is to add them, divide by 2, take the average.
Oh.
There's a little quicker way though. There's 60 apart, so the middle must be 30 from either edge.
Alright.
Right? So you do the same work with number 11.
Alright.
Okay, any other homework questions before I do my thing? All right. So if it was normal and I knew this population standard deviation, I could then use
T-scores.
Z-scores, right? I only have to use T-scores if it's normal, but I don't know the real standard deviation.
What if n is greater than 30? Do you have to know that it's normal still?
Well, that's how I know it's normal.
Oh, okay.
So how do I know it's normal? N greater than 30, or they say so.
Because on the homework there was a question and it was like n was greater than 30, but the population was very skewed. But they in the answers they expected you to just to use T-scores. So that's what I was asking.
Oh yeah, yeah. So no matter what the population looks like, that 30 is the magic number. And we saw the one that looked like that. And once you get to 30, it actually will end up looking like that. Yeah. So 30 is the magic number, no matter what the population looks like.
Okay.
Now, if they say the population looks normal and n is less than 30, you can still use T-scores if you don't know the population standard deviation because it's already starting off normal. Is that cool?
Yeah.
Okay. Cool, maybe. So both Z and T require normal. How do you know it's normal? They either just tell you it's normal. That's nice. Oh, it's normal, sweet. Or they don't say a damn thing about normality, but the sample size is bigger than 30. Then you know that the sampling distribution is normal enough, and you can keep going. Cool. Okay. The big key here is T-scores are new. They were invented to cover us for this. That's when I use them. And the cool thing, you can see that in the formulas. Z goes with sigma. T goes with S. So don't let you write notes on your formula sheet, but the formulas themselves are notes.
Those look the same.
Okay. You'll be all right. Okay. Focus on important stuff. So any more questions from 7 before I get back into... Actually, I want to do a couple of quick T-score examples. So if I had... Actually, let me make this a little more specific. If n was 81, and S is 1.97, Do I use a T or a Z?
T. Use T.
Yeah, why?
Because we know S. We don't have that.
Yeah, I don't have the population standard deviation, and
Yeah. And
it's normal because the sample size is big enough, right? So now, which T would I use? So I use a T score. Good.
yeah.
Which T would I use?
With our error value.
Yeah. So now I'd have to say, now that we know we can use a T score, if I want a 99% confidence interval.
N minus 81 minus 1. 1 minus 81.
What's that?
Are you telling us you want a 99%?
Yeah. If I want a 98% confidence interval,
So you wouldn't have been able to do it once.
not yet.
Okay.
Now you can. What T score would I use? So what do I have to know first?
DF. The
Degrees
DF.
of freedom is
1.
yeah, 81 minus 1, 80. And that's what this side of this chart is. So this is a chart, it's actually a little easier to use than the Z-score chart, to be honest, because you don't have all these second decimal places running up here. What you do have to get used to, though, is if I want a 99% confidence interval, where do I look? How much would be outside then?
0.5. 0.5.
1% or 0.5% in one tail. Either way you look at it, 1% in two tails, 0.5% in one tail. They both take you to the first column. And then you just stop at 80 as I make my camera fall away. Stop at 80. So right there, 2.639.
So you said you always want to round down if you get a number not on the chart, like 120, 130.
Yeah, exactly. You round down just to be more conservative. The whole idea of T-scores is to make the Z-score a little bigger than what it would have been to cover you. So if your chart doesn't have specifics, you want to just, when you have to make an error, when you have to choose one way to go or the other, you choose the more conservative way. So what if I had the same kind of setup? So we still want a 99% confidence interval. N is still 81, but sigma is 1.84.
And they use a Z-score.
Yeah, because why? Two things. Why do I use a Z-score now?
You know the standard.
Because we have standard deviation.
Be more specific. I had a standard deviation here too.
You know that's the population.
I know the population standard deviation, and I know that this is normal because the sample size still is big enough. So what Z-score would I use?
And on the chart.
So this one.
Yeah, and in fact, you could look at this chart. This is so cool. I know this is a T-score chart, but Z-scores are on here. And this thing is set up beautifully for confidence intervals, right? So if I want a 99% confidence interval, I'll look here. I want a Z-score, so look all the way to the bottom, 2.576, which is just one place off from 2.575 that we were using earlier because that was a little bit rounded.
Why do you look all the way to the bottom?
Because what's all the way at the bottom?
Z-score.
Z-scores.
Or large.
So the whole idea of T-scores, why were they invented?
For the true mean. We want to find the true mean.
Ass covering, I like it. To cover our ass for when we don't know the real standard deviation of the whole population. So the larger our sample gets, the less ass covering we need because the more sure we are about our standard deviation. And you see how the scores are getting smaller and smaller and smaller. And when my sample gets large, then they're basically Z-scores. I don't need to make them any bigger than a Z-score because I don't have to cover my ass at all anymore. My sample is really large. They purposely make it big because it kind of depends on your population size. We won't get on all of that. How are we doing so far? So T-scores were invented because when we take a sample and I get a standard deviation from a sample, is that going to be the population standard deviation? Most likely not. The smaller my sample is, the less certain I am about that. So I have to be more and more conservative. So my T-scores have to get bigger and bigger to make my intervals bigger. To catch more stuff, to be a little more sure. So the bigger my sample gets, the smaller they get, until they get all the way, they just become Z-scores here at the bottom. Okay, cool. So in this case, I would use 2.576. Or you could use 2.575, that's what we used before. Cool. They only did this because on the Z-score chart, they averaged between 2.57 and 2.58. This is actually the true z-score in this case. It's a little more precise. If you use either one, I don't care. They're basically the same. Okay. Yes, sir.
What is S?
What is S?
And
Standard deviation of the sample. I love it. Yeah.
So will you always look at the large
If you want a z-score, you can look at the large.
for any situation?
Well, for which situations?
For population?
They better be these situations, or else you can't use this.
Okay.
Right? So if I ask for a 93% confidence interval, you can't use this. Right? There's no 7% in two tails.
Yeah.
But this covers basically all the things. There's a 98%, 99%, 95%. It covers basically all the confidence intervals that are normally used. You know your teacher's going to give you one that's not on there. Oh yes. Just make sure you can do it the old-fashioned way. Right? Back on the z-score chart. Okay. All right. So this is a little bit easier to read, I think, than the z-score chart was to begin with. I know the z-score chart now should be easy to read because we use the hell out of it. But this one's actually a little bit more direct. Okay. So any questions from that? Yeah.
I was looking at the top of it. Why is 1 degree of freedom like 3 times or 7 times as much as 2?
Because if I only take a sample of 1, I mean a sample of 2 is that many times more information. It's not really just twice the information, because if I take 2 people, I could randomly pick a very tall person. If I go out and pick another person, it's less likely that I also pick another really tall person. They should kind of average each other out. They should tend towards the average. All right, so samples start to approach the average even at a sample size of 2.
Why is it such a big difference from 1 to 2?
Because it's not a linear relationship.
Wouldn't it be from 2 to 3?
From 2 to 3, yeah, sure. Yeah. So it's not a linear relationship. That's what that's showing, right? So once I add a third person in, now it's really hard to escape the average. So every time I take another person, it gets harder and harder to escape the average, to really be far away from the average. So I'm much more certain that I'm closer to what I should have. Okay.
Can you do an example with the following?
Yeah, sure.
Is this still 7?
This is still 7
Okay.
on
7 by 4.
What is the word before spend?
amount. Yeah, that's me trying not to write so many letters. So an average amount spent on Black Friday of $251.49. This is like last year's Black Friday, not hit Black Friday. Also, and standard deviation of $87.11. So we took a sample of 47 people. We say, how much did you spend last year at Black Friday? And they say, whatever. I spent $1,000. I bought 80 TVs. So we find an average of $251.49. And the standard deviation amongst those 47 people that we polled is $87.11. How are we doing so far? Okay, I think that was good. So now I want to know what's the 98% confidence interval for the true mean dollars spent last year on Black Friday. Now some of your homework is going to be very specific. In fact, some of your homework is going to say S equals blah. And if they say S equals blah, you're like, okay, T-score. because they don't have sigma, I only have S. But what is it here? I didn't say S equals blah.
Said take a sample.
Took a sample, but more importantly, my standard deviation came from that sample, right? We took a sample, we find an average amount of this with the standard deviation of that. That came from the sample. People very often, for some reason, when people do this problem, I see them say, we know the standard deviation is this, so I can use z-scores. No. Which standard deviation is it? That's the question. Which standard deviation is that? The sample standard deviation. So what else goes along with that to tell me I can use t-scores? That I have to use t-scores. It's normal. So 1, normal, n equal 47 bigger than 30. 2, sigma unknown, t-scores. Cool. Okay, so that means I'm going to use this formula here. I know S, I don't know sigma, so that's another check that I have to use a t-score. So the only thing I really need to look up, because I got everything else, I got N, I got S, I got X bar. The only thing I need still is my t-score. So what do I actually look up to find that t-score?
The sigma isn't this the standard deviation?
That is the standard deviation of the population. Do I know the standard deviation of the population? No. I know the standard deviation of these 47 people. I know the standard deviation of the sample. I know S. Cool. Right? Greek letters, population, our letters, sample. I don't know the population standard deviation. I only know the sample one, so I must use a t-score. It's going to do its job. That's what it was invented for. So how do I look up that t-score? What do I actually have to look up?
1 minus, or 47 minus 1.
Yeah, so the degrees of freedom,
47.
47 minus 146.
We go to 46.
Mhm.
And then
And see, what's the closest I can get to 46, really?
3%.
Good, so I look at 45.
Yeah.
I want a 98% confidence interval.
2%.
Good, so 2% outside if there's 98% inside. So I want to be right.
So how many decimal places do you want us to round to for this?
2.412.
Let me catch up to you. 2,412, right? I'm going to use this here formula.
Normal.
The t-score is 2.412. Cool.
Greater than 10.
Alright, so this is for 98%, so that means there's 2% outside, there's 1% in one tail. Either way you look at it, it's going to get you to this column here. So 2,412 for degrees of freedom of 45. And now I just got to plug and check, right? Which is a way that I never teach, but once you suffer through all the concept, you can now start to look at it like that. Identify what I need, and I start to plug the right stuff in the right place. X bar was 251.49, give or take this many standard deviations. 87.11 divided by the square root of
47.
47. Cool. So let's all try to do this error first together. See if we all get the same number. Just the error part. On this one specifically, since this is money, you can go ahead around to a couple places. That's fine.
2 decimal places.
In general, you go one more place than this. When in doubt, just go 2 or 3. It should be enough. So what do you guys get for the error?
30.65.
Yeah, 30.65. Rounding it up to 2. So how do you get your interval? Yeah, subtract it and you add it. Cool. I love that one year when somebody asked me where that plus or minus button was on the calculator. Okay, I'm sorry, buddy. It's just 2 things you got to do. 251.49 minus 30.65 is 220.
0.84.
Thank you. 214.
Do you want us to write it like that, or do you want us to write it like the left?
Well, that's so far so good.
Okay.
Now, how do I write the expression? How do I write the little statement?
We confident 19%.
Yeah, we are
Confident.
98% confident that the interval
contain between two.
But do you want us to
two
write it with the
0?
less than, the mean,
2 0.
and then less than 282 or
Contain-
whatever?
no, just
No,
like that's fine.
Okay.
We're 98% confident that the interval blah 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 does what?
Spend the money. The money. Contains the.
Contains the true
mean
mean amount
amount
spent. That's
Black
the right
Friday.
amount, sorry.
Black Friday.
Spent last year on Black Friday. And yes, you must write this conclusion at the end. One part of statistics is being able to do the work. The other, slightly more important part is being able to interpret what the hell you just did. And then past that would be explaining it to other people so they can understand what the hell you just did. Right? Okay. Alright. So not a huge difference there between section 7.3 and section 7.4. One you look up a z-score, you plug it in there, you do this. The other one you look up a t-score, you plug it in there, you do this. They're just about the same thing, just use a different chart. Okay. So, last time, I probably freaked a few people out if you happen to look at this. I'm going to desperately try to. You might have given up very soon into it because you're like, null and alternate. Well, okay, I'll just wait. But the whole idea of this is to give a more precise way to test a claim, to see if a claim looks to be right or looks to be wrong. And actually, at the end, we're going to get a much better definition of how right or how wrong it seems to be. So far, we've only been able to say, is it unusual or not? Does it look wrong or not? We haven't been able to say how wrong it really looks. So we got this here?
Yes.
So, let me kind of step into this. Let's see, what kind of a example do I want here? I want to build off of stuff that we already know. Actually, let's go ahead and do this. We might as well do the thing that's on here. Everybody has one of these here, right? Somewhere floating around. I have extras if you need one.
What is this worksheet? Hey.
Sure has two sides to it. So there's a couple of terminology things to get over here, and they're not huge, hopefully. Turn you around. Okay. Yep. So just read through this real quick if you haven't read this already. This might be a subject near and dear, or near and dear might be the wrong phrase, but I'm sure we're all having possibly some kind of credit card debt, or you guys might be experiencing student loan debt, which is a little bit better to have because it's better interest rates. But do you see the idea here? So the average credit card debt on this day a year ago was that. We believe this debt has increased. I actually took these numbers from a report that was released like a week ago or something. So this is roughly true. I had to make up some kind of a sample that was close to what they're saying. So from a sample of 74 Americans with cards, credit cards, we find a mean debt of $48.97. So why is that not enough by itself? I mean, we believe this debt has increased. We feel that the debt it was $46.72, and we think this has increased. So we take a sample and we see 74 people gives me an average of $48.97. Now right there, what the hell? Why would I do all these freaking 5 steps when that's bigger than that?
Because it's
What's
a
wrong with you, Jeff? Right?
So it's a sample.
Yeah, it's just a sample. It could very well be that the sample I picked happened to have higher credit card debt holders. I mean, even if I do it randomly, even if I pick something randomly, there's always a chance that I get it to be higher or lower than the mean. In fact, I can put money on the fact that it won't be equal to the mean. So it's got to be on one side or the other. So really, this whole thing really boils down to, is that so far away from this that that's evidence that this is wrong? Let me say that again. I've been saying that kind of thing this whole semester. I've been trying to get us ready for this because this is the one that always kind of trips students up. I think it's mostly because you got 5 steps in front of you. When you start a problem, you're like, shit. Is this so different from this that we have to say that it looks like this is wrong? So for example, if I had, here's the 4672, right? And if I took a sample and I found a sample right there, is that really far away from that?
No.
No. But if I found one that was here, is that really far away from that?
Yeah.
Yeah, it looks really far away. We're going to be a lot more precise, obviously. We're not just going to throw it up on a visual and say, yeah, it looks about far enough. We're going to be very specific. And what are we going to use to determine how far away it really is? In what way are we going to use those? Z-scores. I love it. So we're just going to calculate the Z-score. This Z-score would be, it looks like even less than 1, right? It looks like less than 1 step away. Whereas this looks to be possibly 3 steps away. Just a rough visual guess. You with me? So somehow the Z-score is going to come into play. And we're actually going to take one more step after that. So at the heart of a hypothesis test is simply, what's far enough away? So let me write this down. Heart of a hypothesis test. 1. What is far enough away to show evidence of something? And then 2, is our sample far enough away? So not everybody here likes football. For some reason I like this example of I'm a coach for a football team. My whole football team is freaking slow as hell. So I need some fast person to join my team. So it can be a wide receiver, a punt returner, or whatever. Somebody who can run the hell away from the other team. So I set a benchmark. I say they got to be able to run this far, this fast. I set a benchmark. Right? I'm really bad with how fast things actually go. So if I say they have to run the whole football field in however many seconds. Anybody play football? What's a good time across the field?
100 yards, like
5 minutes.
12 seconds.
12 seconds? All right. So I say they have to do it in 11 seconds. I want a fast, kick-ass fast dude. I'm crazy. So I set my benchmark, and then I start taking people come in, and I see, did you meet the benchmark or not? Did you meet the benchmark or not? Is it evidence that you're really fast or not? That's exactly what we're going to do on this kind of problem. Is this sample so far from this that it's evidence that they've gone beyond? That the mean really isn't here, that it's really moved up? Maybe. Okay. Yeah?
What is a 74?
74 sample size, right? If I remember correctly. Yep.
Oh.
Sorry, buddy. So from 74 people, we got this. The reason I can't just stop right there and say, well, there's evidence, is because I don't know if that's big enough of a difference. Okay. So we know eventually we're going to have a step where I'm calculating Z-scores. And we know eventually I'm going to have to set. So right now we have a benchmark that we've been using this whole time. Our benchmark has been a Z-score of 2 or negative 2, right? And then beyond that is evidence that something's weird. Anything within that is everything's fine. Now is this time. Remember back then I said it's not always going to be 2. It's going to be dependent on what the situation is. So now we can change that. Okay. So the first step is kind of a new step in a way, but can you, what is the claim that's being made? I basically already said it. What's the claim that somebody's making in this? And we're making it. we believe,
The debt is increased.
yes, so the average is bigger than, it's increased, right? So we think the average has gone up from what?
From 4,672.
I love it. 4,672. So we think the average has increased from last year. So we think it's bigger than 4,672. Cool. So inside this test, you're always going to have a position that will prove something. So in order to prove something, I have to be either way up here or way down there from the mean. I have to be the part that says way down there or way up there, right? In order to prove that something's wrong, that something's different, right? And the other side's going to be, no, it's in here, it's fine. I'm inside the usual area, I'm fine. There's going to be two statements I can kind of set up. And the first one's called the null hypothesis. And the second one's called the alternate hypothesis. In my old book, I used to have HA there, which made a little more sense. But this book wants to use H1, so I'm just going to adopt that. Okay, so this is not that huge of a deal here. Here's the idea. H1, and I know it's going to be really hard for you guys right now. Let me just say this to you. It's going to be really hard right now to determine what's really important and what really isn't that important. So give yourself a break. Don't. As we do more of these problems, you're going to pick up what's really important here. H1 is the one that's going to be able to prove something. I'm going to either support H1. H1 is going to support that I have evidence, or it's going to fail to support that I have evidence. So this is the one that's going to show evidence. Which must mean this is the guy that's going to be in here somewhere. And what that really boils down to is this was the one that's got to have the equal to statement in it. Right? The equals has to be here. So if this is one of these statements, what's the opposite of this?
Less.
That's what that is. What's the opposite?
Less than.
Less than
4, 5,
or equal to.
Equal to 4, 6, 7.
So where should that statement be? The equals must be here.
Alternate.
He must be the guy that's cool with it being close to the mean. He's the guy that says, if you show this is true, then I haven't shown evidence for anything different. The status quo. It's the same as it was. So this will be mean less than or equal to 4672. This is the one that then must be this, the greater than. Bless you.
Wait, isn't that our hypothesis?
This is our claim.
Yeah.
These are our two hypotheses.
Oh.
This is our claim.
So the claim is the alternate?
Yes, cool. The claim could be one or the other. If my claim was the mean is 80, mu equals 80, that has to have the equal sign, that would be HO. Why is the claim H1 in this case? Because it did not have an equal sign. So either one of these could be the claim. Why is the claim this one in this case? It does not have an equal sign.
Just put the equal sign? Or?
Yeah, to get the opposite, of course, yeah. The opposite of more than is less than or equal to. Is that cool? Okay. Somebody's got to have the equal sign, or else you're leaving that poor dude out. He's got to be on one side or the other. Okay. Give yourself some time. This takes a little time to get used to. So you're all like, damn, that's step one. Shit. But step one was loaded with kind of new stuff. Hypotheses, their names, how to tell where to put what. Okay. Step 2, 3, and 4 are going to be very familiar. Thank God. Step 2 is really just, what am I allowed to use to test this? Can I use z-scores? Do I have to use t-scores? Or can I use nothing? And what do I look for to tell me? What's the first thing I really should look for to tell me I can't do a damn thing?
If it's normal.
Is it normal?
Yeah.
Z, T, or nothing. Is this one normal?
Yeah.
Why?
Greater than 74.
And is 74 bigger than 30?
Everything.
And then what do I look at secondly to tell, now I know I can use something, how do I tell whether to use Z or T?
Standard deviation.
Yeah, which standard deviation do we know?
The standard deviation of the sample. The average, the American. Standard population one.
Yeah, the 954 is from the population from last year, right?
Yeah.
So we know the population standard deviation. We know sigma is 954. Did that 954 come from my sample? No, so it must be the population, and it is kind of worded to be the population standard deviation from last year, so we're going to use it again this year. That's a big assumption to make, but just go with it. So pretty cool so far. So if I would have said, from a sample of 74 Americans, requires we find a mean of this and a standard deviation of this, that would have been a sample standard deviation. I would have to use t-scores. In this case, what can I use? Z-scores. Cool. So real quick word on the homework. Section 8.4 is Z-scores. Section 8.5 is T-scores, if I remember correctly. So they're both the same setup, the exact same setup. This step will be different though. It's a T-score, but the rest of it will be the same. Right? So they really could have put those in one. So you just get a little more practice. So I can use Z-scores. Step 3 and 4. So you guys are still with me. It's a lot to suffer through, I know. Step 3 and 4 are related to that heart of the hypothesis test I talked about earlier. Step 3 is going to tell me how far away is far away enough. And then step 4 is we're going to look at the sample and see if it made it far enough. So if I said, this is far away enough, and my sample gets here, that's evidence that this is wrong. If my sample gets there, I didn't make it far enough away. I failed to find evidence that it's wrong.
Wait,
That's the idea.
Try that again.
I will. Let's say it through this here.
Okay.
On step 3, I know I can use Z-scores. What's the alpha? Remember good old alpha?
Yeah. The error.
Yeah. Alpha is 0.05. Now, can somebody tell me, and this is something I forgot from this up here, how many tail tests do you think this is? What side of the picture am I interested in? And I keep doing it whenever I do a problem like this.
One side.
I'm only interested in the one side, right?
Yeah.
This is a one-tail test. A two-tail test would be mu not equal to something. If it's not equal to, it could be less than or greater. But if I feel it's increased, if we feel it's gone down, if I feel whatever, that's going to be a one-tail test. In this case, it's one tail up here. Now do you see why that T-chart is set up beautifully for hypothesis tests? If you want a one-tail test, you look at that one. If you want a two-tail test, you look at that one. So this is a one-tail test.
Can you explain again, sorry, why it's one tail?
If I want to show that the mean is bigger than this, I only want my samples. The only samples that can show that would be up here. So it's only that tail up there is the only thing that's going to show evidence.
So what would be an example? It would be the opposite of that.
A two-tail test? A two-tail test would be, we feel it has changed. What's changed mean? It could have gone up
Down.
or down. Then that would be a two-tail test. Either tail would be evidence.
So if you saw the word change, that would be.
Yeah, either changed, yeah, that one's a little bit
something
evil.
that's different, like altered.
A one-tail test is always very obvious. They think it's increased. We feel it's gone down. We feel that there's less. We feel that there's more. That's very obvious. A two-tail test is more hidden sometimes. Right? But again, we've only done not even half of a problem yet, so we can't start seeing patterns yet. So how to tell what's going on. So I know I can use Z-scores. I know it's a one-tail test. Alpha's 0.05. So one-tail test, right? This is beautiful now. You guys will start to realize how cool this is. One-tail test, 0.05. Where do I go for a Z-score? All the way down. If I stop, I get a T-score. I go all the way down, 1.645. That should maybe sound familiar. We've seen that Z-score before.
Oh, for 90.
Yeah.
0.05.
For 90, but in this
Exactly.
case it's for 90.
Because if there's 5% in one tail, there's 10% in two, that would be 90%. So Z here is 1.645.
Where did you get 0.05?
It's given to me. At the very end here. Right there.
Oh, you know the worksheet.
Yeah. So has everybody got this guy here, right? Okay. So don't worry. This thing is loaded, I understand, but I was trying to be very descriptive in every step. So I'm thinking if I were you, I might have it sitting next to me as I'm doing my first couple of hypothesis tests. It really describes what the hell each step is all about. So now I know.
So it's as if they're rolling.
Yes, ma'am.
The reason we're using a z-score is because we have the population one too.
Population standard deviation is known, so I can use a z-score. It's normal, yeah.
Right now, did you just use a z-chart or the t?
I use the t's, but why is that okay? Because not because it's large, but because z-scores are down here. That's all. Do you understand? So I don't have to stop at 70 something or other just because n is 70. I want a z-score. If I stop, I get a t-score. So don't stop. Then I get a z-score at the very bottom. So if you want to, write in here z-scores, right? Maybe with a normal pen and not a mark. Yeah, cool. Okay. So this is step 3, defining the rejection region. Actually, kind of meant to do it up here. That's all right. So I know that this is my rejection region. That's far enough away to show evidence. So this is what's called the rejection region. I know. And the reason it's called that is if I find a sample that's in here. Let me see if you guys are kind of with me. If I find a sample that is way the hell up here, which one of these is wrong? Which one of these looks to be wrong? It's evidence that it's wrong.
HO?
Yeah, this guy is wrong then. I'm so freaking far up that way, there's no way it's equal to or even less than. So I can reject, you're going to love this. You ready? You can reject the HO, the HO.
Because
You can support the high.
she was found in the
So
rejection.
however you like that combination of phrases is great. So reject the null, support the alternate, if you'd rather stick to purely technical terms. You guys kind of with me? That's why it's called the rejection region. If I get out that far, I can reject this guy, which means I've shown evidence that this guy is right. Is there a chance I'm wrong?
Yes.
And actually the chance I'm wrong is exactly 5% chance, right? Just like before. So statistics, very honest. Every single problem, there's some part of the problem that says, there's this chance you're wrong as you're doing this, buddy. Yeah, all right, dude. That's real life. People hate it because it doesn't give exact answers, but get over it. You never get freaking exact answers, ever. So it's the most honest math there is. It's like, dude, I have no idea. We have some idea, though. 5% chance I'm wrong, that's awesome. That's better than normal. 95% chance I'm right. What the hell? I can live with that, right? Okay, cool. So to make this into a statement, you guys are going to love this. All right. So this z-score right there, that z-score is just the benchmark. It says any sample you take has to get beyond this to show evidence that the mean is wrong. You guys with me so far? So this one is the z-score. In the book, it's called the critical score. Right? Just in case you see that in the book. Critical score kind of makes sense. It's that boundary between evidence and not. The z-score that I'm going to get on the next step that actually is my sample z-score, I call it z-star, just to separate it, just to give it its own little symbol. So I can say right here, if my sample z-score, let me just write this out and see what you guys think, is bigger than 1.645. If my sample z-score is bigger than 1.645, what did we just say earlier that we can do? Reject the HO, right? Reject the HO. Always. You guys kind of with me? Because we made it into the rejection region then, so therefore I can reject the HO. I can support the H1. Yes?
So what if it's like 4673? Because isn't that greater than HO?
It is, but is that far away from HO? The whole point of this, the whole thing behind the scenes is we're only working with a sample. In order for a sample to be evidence of something, it's got to be that much further away.
So is it arbitrary, or is there a specific?
To a degree, it's arbitrary. Which is why we go one step beyond. So just boom. So if Z star is bigger than 1.645, we can reject the HO.
What is Z star?
Something I made up. And I'll show you. It'll be a loop here in a minute. Just give me a minute. If I can say this dude's wrong, then I can say this dude looks to be
Do
Right.
you want us to write that in step 3? Still,
Yes,
you're not
I
in
do.
step 4 yet?
Not yet.
Okay.
So if Z star is greater than 1.645, I'm so far away from the mean that this guy must be wrong. It looks like this guy's right. So if we do get a Z score of more than this, we reject the H naught, we support the H1. Okay. So this is long and tedious, I understand, but just go with me here. Okay. Some of you guys look like you want to hurt me. So in step D, it kind of makes sense. If I've set up how far my sample has to get away, the next thing I want to do is see how far away did my freaking sample get. Did it get far enough away or not? So the next step is look at the sample information. Don't worry about this guy. We'll talk about this guy in a minute. So what's my sample? What do I know from my sample? I know that N was 74. What else do we know from the sample?
The sample mean is 4,897.
I love it. So the sample mean we got was that for credit card debt. What else do we know? Nothing from the sample, but we know the standard deviation, right, was 954. Cool. Before I make a Z-score, what must I do?
Wait, don't you use S, not the...
No, we know sigma.
Oh, okay.
Yeah.
Okay.
Right, we knew the standard deviation of the population. So I've got sigma. Now before I make a Z-score, what do I have to do with something here? We took a sample, and we're talking about the sample means. Therefore, I must... I'm not asking for a confidence interval, right? So you don't have to worry about any of those formulas there. But whenever I take a sample and I ask questions about the sample mean, what must change? Standard deviation. So that just make it a step. This is an automatic part of this step. Find the new standard deviation. All right, so it's the old one divided by the square root of the sample size. So somebody help me out there.
110.9.
Go further.
That's it.
Oh, really? 900?
Yep, 900.
Sweet. Freaky. Because remember, these always have to go at least 3 places, and if it's 00, just to cover yourself, put that. All right. So this step, again, this step is really old news. It truly is. It's just in the middle of a bunch of new shit. So we don't see that this is old. We should be able to do this problem. Get the Z-score. Z-score is always our data. Our data was a 4897. Minus the mean, and we accept this to be the mean at the moment. Because here's the idea. If somebody said to you, I can bench press 400 pounds. Like, all right, I'll assume you're right. Go do it. And then we say, well, there's evidence that you can't do it. You couldn't. We go in there, we set it up. Oh crap! So there's evidence you can't do it. So I say, okay, assuming you're right, what the hell just happened? Assuming that you're right, why did this just happen? Right. So we go into this whole hypothesis, assuming that that is the mean. Let's assume that's the mean. Sure, what the hell? And we're going to have to, we want to get something that, look at what we did. Assuming that's right, why is my sample so freaking far away from it? That's what we want to be able to say at the end. So that's why on this step, what do I put here? The number that was in my hypothesis, 4672. So that is the mean. And then divided by that new standard deviation we got.
So 4,897, that's basically like X.
That's X.
Minus the mean.
And that's really, to be honest, this formula we're using is, remember this guy, it's x bar minus mu sub x bar over sigma x bar, all that crap. But the z-score formula never changes. My data point minus the mean divided by the standard deviation, whatever those things are. Right? So my data point minus the mean divided by the standard deviation, it's always the same formula. And then what do you get for that? 2.03? Cool. So where does that fall on our picture? This is Z star, by the way, sorry. Where does that Z star fall on our picture?
Past 1.6.
Yeah, it's in here. It's 2.03. Put a little star there for a nice little visual. So our sample was, the sample we took randomly, the 4897, which is not even up here. The 4897, the sample that we got, ended up being so far away from what they thought the mean was, the 4672, that there's no way it's that. It's so far away from this that there's no way that the population is actually this. Because anytime I take a sample, it's probably not going to be the mean. But this sample was so far away from what the mean is supposed to be that that can't be it. That can't be the mean. The mean must be higher. Can we say that the mean is actually this now?
No.
Hell no, because that still just came from a sample. That sample is enough evidence that it is bigger than what it was. But it's not enough evidence that it is this, right? It's easy to disprove something, not to prove something.
So, because that 2.03 is bigger than that 1.645, we know.
Exactly. 2.03, bigger than 1.645, we reject HO, which means we support H1. Okay, right?
So is that step 5 where we put that? We're rejecting Joe? Okay.
That's still step 4. Step 5 is going to be, and I'm going to come back to the p-value. I want to get one more example in here before you guys leave. Step 5, step E here, would be something related to, it's not the same wording as the confidence interval, but it's going to be about as long. Here we could say, did we find evidence or did we not find evidence? We found evidence. It was significant. It was far enough away. So we have found evidence. We have found, I'm forgetting all my words. We have found significant evidence to do what? Which one's my claim? You always go back. Which one was my claim? HO or H1?
Claim was H1.
The claim was H1. It could be either one, but in this case it was H1. So I want to use this language then. I always want to write my conclusion based on my claim. So support the claim. We have found significant evidence to support the claim. And then you just go back up to what the claim was. The claim that the debt has increased from 4672. The credit card debt has increased from 4672. So you have to put something real from the problem. You can't just say, we found enough evidence to support H1. No, you have to give me physically what the hell does that mean. So let me see if I can sneak one more example in here. Yes, sir.
Is this going to be on test? Yeah. Oh, this chapter, sorry.
Yeah, I never put information from one day on the quiz the next day. Have you ever noticed that? So this won't be in the next quiz. Just confidence intervals. So we're going to try to do number 1. We're going to do this together. And a quick word on how what we're doing relates to where we are in the book. This is section 8.4. 8.3 is about testing percentages. 8.5 is about testing means with t-scores. Right? So 8.4 is about testing means with z-scores like we just did. 8.2 is kind of like a bunch of basics of all the problems. You with me? It's kind of like all the parts of the problem, they really flesh it out.